Hello, welcome to Miranda project demonstration. Here we can see the overall architecture of the integrated Miranda components. In the presented demo, there are two different flows for the different type of data collected. We can see in the image with blue and red arrows the flow for collected logs net flows. The first component to demonstrate is the context discovery component. The visualization of the context discovery component has been integrated into LogScale platform. The platform fetches the generated information about the services, the context, and the pods running in the cluster from Kafka. In the upper part of the screen, exploring the graph, we can see the different assets and how they connect to each other. In the generated graph, the nodes represent the assets and the edges represent the flows between them. Such assets that are visualized as nodes may be APIs network functions, network nodes, etc. The different lines that are the edges between them represent the different type of flows that exists. Such flows may be control flows, like the ones with the blue lines are visualized here, or packet flows, like the ones with yellow dotted lines. In the top right part of the view, there's the scan button, where it can instantiate a scan in the Kubernetes cluster and refresh the generated graph with newly discovered assets. Hovering the mouse over a node or an edge of the graph, we can see some compact information about it. If we select a node, we are able to see more information about the specific node. For example, we select a node that is kind of host and represents a running instance of a MongoDB database. The next part is the attack paths component. The attack path component is receiving vulnerabilities from the threat feed connector components and produces as output a list of potential attack paths that is sent directly to the LogScale platform for visualization. The whole extraction, threat modeling, and threat analysis pipeline of the attack paths component is fully automated, requiring no manual input. It starts by fetching the latest service context graph from the Kafka topic. This graph doesn't carry any security information yet, so the first thing to do is enrich it. It gets sent to the threat correlator, which goes through each service and annotates it with the vulnerabilities it's exposed to. That enriched graph is then converted into a Prolog knowledge base following a custom threat modeling taxonomy. Every service, vulnerability, and relationship gets a formal representation, and that's the input the reasoning engine needs. From there, the engine applies formal derivation rules to infer security properties that aren't explicitly stated, but that can be logically derived from the known facts contained in the knowledge base. Every new fact gets added back into the knowledge base, which can in turn unlock further inferences. This keeps going until the engine hits a fixed point. No new facts can be derived. Reasoning is complete. And for every derived fact, the engine records the exact chain of reasoning that produced it, which is what makes the attack paths traceable and explainable. Once inference is done, we pull the results. Here, the engine derived 131 facts split across 3 categories: services that can be made vulnerable, services that can malfunction, and services that can be compromised. All of them are browsable in the right-hand panel. Let's take a look at a concrete multi-step attack path example. We select the fact that UDM_netfun_nat can be compromised via callback hijacking, and the component builds the full derivation tree behind it. Reading from right to left, UDM_netfun_nat is exposed to CVE-2026-27642, which is exploitable via information disclosure, so the engine infers that the service is vulnerable to that threat. From there, since nothing is defending against it, it concludes the service can be compromised. That compromise, combined with the fact that information disclosure causes data exfiltration, leads to a further inference. The service is malfunctioning, suffering data exfiltration as a misbehavior. But the chain doesn't stop there. Data exfiltration in turn induces another CVE, exploitable via callback hijacking, making UDM_netfun_nat vulnerable to this second threat as well. And again, with no defense in place, the engine concludes it can be compromised by callback hijacking too. Every step in the tree is a formal reasoning step. The leftmost node is the final conclusion, and everything to the right is the evidence trail that supports it. Moving on, we will present an example of some security agents. We would like to note at this point that the integration of the management of the agents in LogScale platform is still under development, as they need to automatically be discovered from context discovery component. For this reason, we will showcase how the security agents can manually be started. In the first part, we show how we can use the context discovery service to fetch the service context graph and the URLs of the OpenC2 agents. First, we perform a context discovery and generate a file called contains the SCG. Opening the JSON file, we can see all the information it contains. Then, we extract the OpenC2 agents from the SCG. As we can see, there are 3 agents: FileBeat, PacketBeat, and FPRobe. Moving on, we show how we can use the context discovery service to fetch the service context graph and the URLs of the OpenC2 agents with the URL discovered in the previous step. First, we ask some information to the OpenC2 endpoint, and it returns its supported capabilities, for example, how to configure FileBeat. Then we start FileBeat, which returns an opaque identifier. When FileBeat starts, it ends data to DHP through Kafka. Entering the container running the agent, we can see that FileBeat is running and launching TCP dump. We can see that we are sending data to the DHP. Moving on to Kafka UI, we can see some of the data sent from FileBeat agent. Opening the message, we can see some detailed information about it. In the agent subfield, we can observe that the type is set to FileBeat, the ONW we used. Finally, we stop FileBeat using its returned identifier from the previous step. The next component of integrated Miranda platform is data handling pipeline. The visualization and management of data handling pipeline is also integrated with Logstale platform. In the screen, we can see some general information about the existing pipelines. In the top part of the screen, we can see various information like the status of configured pipelines, along with their configured sinks and sources grouped by their type. Configured pipelines are also listed below with their configuration information about the sink and source type and their status. At the side of each list item, there is a Details button that shows all the required details and configuration of the selected pipeline, and a Stop button which disables the pipeline. Through Logstale platform, we can create a new pipeline and have it running in the deployed instance of data handling pipeline. When we start the process of creating a new pipeline, a form with all the required steps is shown in the dashboard. In this demonstration, we will create a pipeline for handling collected NetFound data. The new pipeline will fetch collected NetFlow from Kafka, which is selected as the source type of this. In the fields below the configuration of Kafka and the topic that hosts the NetFlows must be filled accordingly. In the next step, the user selects the transformation actions that needs to be done in the collected data. In our case, we select the Enrich transformation. Then we need to configure the sink of the pipeline, which is its output. The newly create pipeline will output the enriched NetFlows in Kafka in a different topic. Finally, in the review step, we are able to see the whole configuration file before starting the pipeline. In the configuration file, we can see all the defined sources, transformations, and sinks we selected in the previous steps. When the pipeline is created successfully, we can see that it is added in the list of running pipelines and its status is set to running. By clicking on the Details button of an item, we can see the configuration file for this item, which describes the defined sources, transformations, sinks options, and the parser that is used for the parsing of collected data. In this example, we see the configuration file of the pipeline that has been set up for collected logs from DetectMate component. Finally, we have set up a dedicated view in Elasticsearch in order to visualize the output of all configured pipelines, grouped by their sink topic. We can see in the dashboard a general view of all collected and processed logs and net flows. In the timeline above, we can see the number of ingested events relative to the time. By selecting an ingested record, we can see more information about this, along with the raw log that produced as output of the pipeline. From the Elasticsearch dashboard, we can also change the time interval we visualize data for, searching back in hours or days if needed. Output of the data handling pipeline component is sent to Kafka. From there, the various Miranda detection engines are reading the data in order to detect any anomalies in them. Miranda has deployed 3 detection engines: DetectMate and Sequential Anomaly Detector for logs and Deep Guardian for net flows. Following up, an example demo of a detection engine Deep Guardian component will be shown. Deep Guardian is a detection engine deployed in Miranda, Response Bible for detecting anomalies in collected net flows. The input of Deep Guardian is the output of the parsed net flows that are produced from NetFlow Parser, which is part of the data handling pipeline component. In the screen, we can see 4 different windows: the NetFlow collector, the Deep Guardian agent, along with the input and output topics that are used in Kafka. In the top part, the Kafka messages from input topic that contain the parsed, and below them, the messages from the topic where the Deep Guardian agent sends the detected anomalies. After some time of collecting net flows, we can see in the collector window that information about initial classification attempt have been received. Then, in the Deep Guardian agent logs, we can see the list with the IDs of the collected flows, which will be used from training a model. Looking at the agent logs, we can see that the training of the model is progressing and soon is completed. The new trained model is saved and loaded for classifying the received net flows. At this point, the GoldenEye attack is starting. After some time, we can observe that the model is producing alerts, sending sticks bundles to the assigned Kafka topic. As we said before, output of all detection engines is sent to Kafka. Additionally, we have created a dashboard in Elasticsearch showing some statistics about the detected alerts from all detection engines, along with the top 50 alerts generated from each detection engine. At the top of the dashboard, we can see the alerts ingestion over time in a specified time window, which is configurable, providing a clearer view of the monitored system across time. Below of it, a counter of the ingested alerts is shown. The counter visualizes the number of the alerts ingested in the system during the time window selected in the dashboard. Below of it, there is a pie showing the percentage of alerts that is produced by each detection engine. In this dashboard, we can monitor that Sequential Anomaly Detector has produced a bit more than 54% of the alerts, DetectMate a bit over 45%, and detected alerts from Deep Guardian are smaller than 1% of the total alerts. In the right side of the panels below the timeline, the top 50 alerts of each detection engine are visualized. Starting from the top, the alerts of Sequential Anomaly Detector engine are shown. Sequential Anomaly Detector takes as input a batch of logs and tries to find anomalous sequences compared with the normal dataset it has been trained on. Below it, the top 50 alerts from DetectMate component are visualized. As we can observe, DetectMate has produced a single type of anomaly over the ingested data that has been detected by the new value detector. This detector is part of DetectMate, which is responsible for searching for new IP addresses that are included in system logs, which were not part of the normal dataset the component trained on. Finally, the last panel shows the detected anomalies on collected net flows that produced from Deep Guardian component. As we saw in the Deep Guardian demo previously, the model is trained on collected net flows and tries to detect anomalies in them. As we can see in this panel, a net flow labeled as anomaly is visualized, providing information about the source and destination IPs and ports. As we stated before, the output of all detection engines are sent to Kafka. From there, the IOC extraction module fetches the detected alerts. IOC extraction component tries to extract indicators of compromise from the detected alerts that are produced from detection engines and enrich them with information from MISP. IOCs are the data that indicate that a system may have been infiltrated by a cyber threat or by an actor. Such data may be an IP address, a host name, a URL, a hash of a file, a registry key, or an email attribute. IOC extraction module writes the identified IOCs in a Kafka topic. Opening the Kafka UI and selecting this topic, we can check the detected indicators of compromise. Selecting one of the produced messages, we can see all the details of the extracted IOC, which in our case is a net flow. For this net flow, we can see information like source and destination, IPs and ports, and its protocol. Scrolling down, we can also see a list of all associated events from running MISP, and scrolling down further, in each one of these events, we can see various information for them like their description or the organization that created this events. IOC extraction component integrates with Threat Sharing API in order to retrieve all these events from the deployed MISP instance. Threat Sharing API is a component, part of the MIRANDA platform, which is developed in order to interact with MISP through API calls. Its main functionality is to fetch and ingest data from and to MISP, making the interaction of other opening the MISP web user interface. In the home page, we can see a list of all the events. These events may have been ingested to MISP either from external feeds that are configured in the MISP platform or from MIRANDA platform components. In the list with the events, we can see the organization that created each event, a correlation number that indicates the number of events this one is correlated with, a short description, and its tags, which help the user to group the events. Clicking in one of the events, we can see more details about it. Scrolling down a bit, we can see all the correlated indicators of compromise that are part of the created event, like IP addresses, the protocol of a net flow, or a simple text. Also, for each one of them, we can see in one of the columns all the related events in MISP platform. Moving on with the last part of the demo, we will demonstrate the Tyrannus AI component, a component used for analysis of threat reports from public sources. In its dashboard, we can see an overview of the total new reports, a quick overview about the datasets that have been extracted from them along with their tags, CVEs, and other information. Moving on the Assess view, we can search among the ingested reports using different keywords or tags or by selecting specific sources from the list of the available ones. In the right side, we can see the matching stories of our filters. We select 2 random stories from the list as an example, and we're going to cluster them. This means that we identify these 2 stories as related between them and combine them by creating a report for them. When we combine the 2 selected stories, we can see an aggregated view of them. From the Actions menu, we select the Share button in order to share the created report to integrated systems. From the drop-down menu of the supported connectors, we select the MISP Miranda connector in order to ingest our generated report in Miranda's MISP instance. By clicking on Share, we can see a success message that our generated report has been shared. Moving on to MISP web user interface, we can see the ingested event in the list of created events in the homepage. By selecting the created event, we can see more information about the created report and the stories that it consists of. Scrolling down, we can see the different tags of the event, and checking them, we can see that a combined story has been generated from the 2 selected reports. Finally, it is important to note that we can add or edit the tags in the created event. So that was the last part of our demo of the integrated Miranda platform. Thank you very much for your attention. Follow us on social media in order to stay informed about Miranda Project.